Okay, guys, 9.3 tests about a population mean. So we've already done some tests. We've already done tests with a population mean. So part 2 of 9.3 is a couple of special cases for tests with a mean. So look at your handout. We should all have that. The very first example is Mr. Wilcox believes that taking a smart pill minutes before a test will improve scores. He takes a simple random sample of 10 AP Stats students and uses them as part of an experiment. Each selected student will be part of the experiment for 2 tests. Before one of the tests, Mr. Wilcox will give them a smart pill. Before the other test, he will give them a placebo. He will randomize the order with which the treatments are given using a table of random digits. Below are the test scores. Okay. So this is different than what we have done before for the mere fact that prior to this lesson, we have only had one sample and we have only had one mean. This problem is talking about taking a student, giving them a placebo, and giving them a test. Then taking the same student, giving them a smart pill, and giving them a test. And it would like us to use that information, okay, to do a test. So my first question is, what kind of design was used in this experiment? Since they are using one student with one treatment and then the same student with the next treatment, they're comparing them. This is a matched pairs design. If you think all the way back to experiments, um, when we decide that we talked a lot about like resting heart rate. I know we did the boot example. When we start comparing the same thing to itself after we've done a couple of things, it's going to be matched pairs design. Okay. So it doesn't really make sense as I look at my data. It doesn't really make sense to have to do something with like just the placebo data. And it doesn't really make sense in my head to do something with just the smart pill data. But what it does do for me is what does make sense is that I would like to know how that student did, the difference on those tests. Okay, so how much higher did they score using the smart pill than they did on the placebo? So this specific student 1 scored 2 points higher when they had the placebo. That's useful information. Student 2, they scored 9 points higher when they took the placebo. Okay, so this difference, that makes sense for me. And the difference that I did was smart pill minus placebo. Okay. So I go down here and I get the difference in those. And then from this data, on average, or the average difference was 4.3. That is useful information. So on average, the placebo pill was showing about 4.3 points higher than the placebo. The smart pill was higher than the placebo, if I didn't say that right the first time. The standard deviation of this data, the differences, the standard deviation of the difference was 5.10. Okay. So how are we going to do a significance test? Well, it makes sense to use the difference, right? So we are going to do a one sample t-test, but we're going to do a one sample t-test on the differences. Okay, so a one sample t-test, we're still doing everything we have always done with a one sample t-test, but this time we're going to do a one sample t-test on the differences. Okay, so when you give this, you are still going to go through all of the boxes like you've been doing. You're going to define your parameter. Okay, so here's the name of my test, one sample t-test, the differences. I am going to say that my parameter is now the average D, right? The difference. So the true difference in the test scores. Then you have to tell me how you subtracted it, because we could have done placebo minus smart. Okay, so I did the smart pill minus the placebo. So you have to tell me that. You're going to have to do that on the actual AP also. Okay, so we're still going to use alpha at 0.05. And we are doing a matched pairs t-test or a one sample t-test of differences. It's the same thing, but matched pairs is a better name. Okay, so matched pairs. When you do this, if there was really no difference between the smart pill and the placebo, when I subtracted them up here, I would have gotten 0. So if the placebo is 91 and the smart pill is 91, that difference would have been 0. Okay? So that's what we're expecting. We're saying that those pills have no difference. That would give us 0. Okay? But what we would like to say is that there really was a difference, and we're thinking that the smart pill makes a difference. So we are going to say our alternative hypothesis is that we think that that difference should be greater than 0. Now, if you change this up here to the placebo minus smart, your ha is going to be that you think it's less than 0, because those would be giving you negative numbers. Okay? You're going to check your conditions just like you always have. However, remember we do have different ways to check when we talk about normal. Okay, so random is still the same. We took a simple random sample of 10 AP students. Normal, we have 3 ways to check normal. The easiest way is if I tell you that the population is approximately normal. I didn't do that. The next easiest way is to look at the central limit theorem. If our sample is greater than or equal to 30, we can say it's approximately normal. But if you look back up at our data, I only looked at 10 students. Okay, so the central limit theorem does not hold either. So the only other way to check off normal is to put all of this up here into a histogram or a normal probability plot, actually plot that on there and show that it's approximately normal. So the histogram of data shows no clear outliers and no major skewness. So the sampling distribution of the average difference is approximately normal. Okay. You're still going to check independent the same way. We want that sample to be less than or equal to 1/10 of the population. Okay, if I'm talking about Mr. Wilcox and all of the students over his many, many years, we can assume that 10 is less than or equal to 1/10 of that population. Okay, so all of those are the same. We've talked about this, but usually n is greater than or 30 always happens. Just know that this can also happen. So then we're going to do our math box. Our math box is the same that it's always been. We have our HO right here. Our null hypothesis was that we believe that there is no difference. So there's our mean, right? And if you go back up here, we found that the average for our difference was 4.3. So we would like to know the probability that we get 4.3 or extreme. Okay, so that's 4.3 away. So if we go 4.3 away down this way, oh, wait a second. We're just talking about greater than 0. So we've been doing two-tailed tests in class, but realize that that's when we had the not equal to. In this one, we are only talking about this greater than there. That's why I have that X, so you don't think we're going down there. Okay? So then you're going to do your test statistic. And the way you do that is if Indra was here, we would ask him. So you're doing x bar minus mu over the standard deviation of the square root of n. Plug it in. You can also do this in your calculator. Okay, so if you go to your calculator, you can find a matched pairs t-test. You could take a list and put all of this information in. So yesterday in class, if you're doing this on Saturday, we did a t-test where you had to put the stats in. You can do this with data. So put these into a list, go to your t-test, and instead of doing stats, do data. Okay? Then you're going to go ahead and conclude. So when you do this, you should get about a p-value of 0.013. So remember, if your p-value is low, you're going to reject the HO. So we're going to compare 0.013 to alpha, which is 0.05. And because that p-value is less than 0.05, we have strong evidence against the null that is statistically significant. Therefore, we're going to reject the null and conclude that the mean difference is greater than 0. Okay, so we have evidence that states that that placebo pill is actually working. Okay, so example 2. You have to add some information in here that I didn't type in your initial question. So this school district has 7,000 students. You need to know that. Okay, so example 2. Suppose that EKHS implemented a new curriculum for the current school year. To see if the new curriculum is effective, the district randomly selects 500 students and compares their scores on a standardized test after the curriculum change with their scores on the same test before the curriculum changed. The mean improvement was 0.9 with a standard deviation of 12. Does the data suggest the new curriculum is working? Perform the appropriate significance test. So again, they took students, they gave them the one standardized test before the curriculum, then they gave them the second test after the new curriculum. So they're going to find the difference in how they did that. So we're going to do a matched pairs t-test. You're going to define your parameter. Mu sub d is the true mean difference in test scores, and I decided to do the new curriculum minus the old. Notice I told you that. You can do it the other direction, you just have to state it. Alpha is 0.05. When I go to my null and my alternative, the null is 0. If there's no difference in those tests, those kids should test the same, so their scores would be the same. That's the claim. We're thinking that the new curriculum will improve our scores, which means that they would have higher scores. So my alternative is that the difference should be greater than 0. Okay, so if you go to your template, the name of the test is match pairs t-test. Randomly selected 500 when I check my conditions. Normal, this time they took a sample of 500 students. So this time the central limit theorem actually works. We have a sample greater than or equal to 30. So we can go ahead and say that the sampling distribution of x bar sub d is approximately normal. You're going to check independent the same way you have. You want that sample to be less than or equal to 1/10 of the population. So 500 is less than or equal to 1/10 of 7,000. Go to your math box. If you find your test statistic, the t, you could plug in your estimate minus the parameter over the standard deviation of the statistic. You get 1.6. If you go in your calculator, you can do this whole thing with a t-test, or you can do t-CDF, just like we do normal CDF, because this is a t distribution, so you're not going to do normal, you're going to do t-CDF. You still have your lower, your upper, and instead of mu and sigma, you have your df, which is your degrees of freedom, which remember is your sample, 500 minus 1, so that's where I have 499 there. Okay, so the p-value is 0.0477. So they're never going to make it that close to alpha. But if you were to conclude on this, because our p-value, 0.04, is less than alpha, 0.05, we are going to reject the null, and we are going to conclude that the true mean difference in test scores is greater than 0. So we have evidence that states that that new curriculum is working. Okay. There are two potential problems with the example that we just did. So because we're comparing the new scores to the test before the new curriculum, we would expect an increase no matter what the curriculum is, simply due to they had exposure to new material. Okay, so that's an issue with this test when we start talking about lurking variables. Number 2, although we found our data to be statistically significant, it might not be practically significant. So remember, statistically significant is when we say that that p-value is less than alpha. What does this mean when I say that it's not practically significant? If this test was the SAT, so use the SAT as reference, out of a 1,600, an increase of 0.9 points. So you get a 1600 and then you get a 1601. That doesn't mean much on the SAT. You would have to increase that score quite a bit. Okay, so practically significant means like in the real world, when you think about context, that increase of 0.9 points really doesn't do much for you. Okay, third example. Mr. Wilcox believes that playing music during class will improve test scores. He informs his classes of his idea and then begins playing music during class. He tells the class that he will measure the results of the chapter test at the end of the chapter. At the end of the chapter, he finds that test scores have improved on average by 4.3%. This is statistically significant with a p-value of 0.03. Identify two potential problems with this experiment. So this chapter test may have been easier than previous. So you guys would probably argue that a couple of Magruder's tests are easier than others. And the results tend to improve anytime the subjects know they're being measured. So for example, when I tell you guys that the check your understanding is going to be a content grade, you guys usually give me a little bit more effort than when I say, you know, just keep it and go ahead and do it. So those are two issues with that. Last example. Each human cell contains a nucleus with 46 chromosomes. Each chromosome has an expected level of protein. Biologists are often concerned with identifying particular chromosomes that may be linked to certain diseases. Suppose that a group of biologists collected protein level data for each chromosome from a random sample of 50 people with Alzheimer's disease. From the sample of 50, they found an average protein level for each of the 46 chromosomes. Then they found 46 significance tests, alpha at 0.05, to determine whether the statistic from the data was significant evidence against the protein level that was expected for the gene. Exactly 2 of the significance tests were statistically significant. So remember, they did a ton of significance tests, okay? So can they therefore conclude that those are the 2 chromosomes that are linked to Alzheimer's disease? So an alpha of 0.05 means that 5% of the time we're going to incorrectly reject the HO, even if the HO is true, right? If we do 46 significance tests, we're going to expect a couple of those to show up statistically significant just by chance, like just by the random chance of how things happen, okay? So just because 2 of them showed up does not give us good evidence to say that those 2 are the ones, okay? So go ahead and finish this up, and we will talk about it in class.